Alicia.
Hi, how are you?
I'm doing fine. How are you?
I'm doing okay. I've been studying. Um,
Uh-huh.
I'm taking a quick stop to my dorm, but I want to show you my notes. But I'm
Oh, yes, yes, yes.
yeah, I'll show you in a
Your
bit though.
notes are so neat. I want to see.
Oh, yeah,
Wait,
I
hold
think
on.
you'll
Hey,
like
Camilla.
this. I came up with like bunch of ways of like understanding SN1,
Yes,
SN2,
yes,
and
yes. I'm
E1.
excited.
But like I'm gonna be honest, I didn't really do the practice exam,
Like you
but
make
I got a
okay.
lot of like understanding on like the mechanisms.
Oh wait, hello, hello, hello. Can you hear me?
Yeah.
Yeah, yeah.
Is
So
it
you,
is it
you
just me?
yeah, I can hear you. You couldn't get to problems, but you made up your own rules and notes on SN2, SN1, E1, E2.
Yeah.
That's good. That's good. I could come up with practice ones for you for us to try and walk through or go over. So,
Okay,
when
that's
is your
great.
exam this week? When is your midterm?
Wednesday.
Wednesday, Wednesday, 2 days.
Yeah, scary.
Hey, Camilla.
Hi,
Let's see. How are you? How are you?
not bad.
Let's see. What did you want to go over in 118C today?
I was wondering if we could go over like Claisen
Hmm.
rearrangement, and
Oh,
then
Claisen rearrangement or Claisen condensation? They're two different things.
oh gosh, okay, I guess both.
Both?
Um,
Okay, okay, okay.
and then I also had a question on I was doing Levin's practice for chapter 22. I just wanted to ask like how you can tell when you do substitution versus like just
Hmm.
um adding it to the ortho para position. I don't know if that makes sense, but
Oh yeah, and I think I know what you're talking about. You don't add anything. Oh, wait, actually, if you talk about the Kolbe Schmitt reaction, you add the carboxylic acid ortho to the phenol. I think you're thinking about like the ones where you think about the strong EWG ortho or para to the leaving group, and that's when you do substitution. And there's some cases where you don't like see any EWG at all, and you can just go for the substitution right away.
yeah.
Yeah. Okay, okay.
I
Let's
guess
let's
if
go
we
over
could
that.
do, yeah, like some practice problems on that, that
Yes.
would be great.
Okay,
Thank you.
okay. Yeah. So for 118C, um, we'll go over Claisen rearrangement, Claisen condensation. They're different chapters. Claisen rearrangement is part of chapter 22. Claisen condensation is going to be chapter 23. We'll go over nucleophilic aromatic substitution. Substitution. Um, and there's two types. There's going to be the types with strong EWG, ortho or para to good leaving group. And there's going to be the one with no EWG, but strong nucleophile or high heat, right? And then there's the Kolbe-Schmitt reaction. Okay, let's do this. Okay, for Claisen rearrangement, this is gonna be an electrocyclic reaction. And this is gonna work with allylic, vanillic ethers, right? And then because we're talking about Claisen rearrangement, let's also talk about the Cope rearrangement because they usually are taught together. Cope Rearrangement. Where an example of an allylic vanillic ether is something like this, right? Where this is an ether right here. This is the allylic position. This is the vanillic position. So this is why we call this an allylic vanillic ether. The reagents that you'll see for Claisen rearrangement is just heat, some high temperature. I'm going to redraw this allylic vanillic ether in a way that is going to be easy for us to draw the mechanism like this. Right? Where this is the allylic carbon, the one carbon away from the alkene. This is the vanillic carbon, the carbon directly on the alkene. If we put heat to it, these are the arrows of the mechanism. It doesn't matter the order, but let's say that I'm shift this double bond to make a double bond here. This double bond is going to make a carbonyl there. And then this double bond is going to make a single bond there. And what that's going to do is create this here. Right. And you could say that this is, if this is the carbonyl carbon, this is the alpha carbon, beta carbon, gamma carbon, delta carbon. We could say that Claisen rearrangement products will always give you a gamma delta unsaturated carbonyl. Right? And that's how you could confirm your product to make sure you get the right product. Does that make sense so far for Claisen rearrangement?
Yeah, so which arrow would go first? I know it's kind of like you, this sounds weird, but you like build it up on the other side and you open it.
Yep, it doesn't matter like the direction or which arrow goes first. We could have went the other way as well. Like we could have shifted this double bond to make a double bond here. We could have broke this bond to make a double bond there, and then we could have used this double bond to make that single bond right there. So they happen simultaneously. Think of it like that.
Okay.
Simultaneously.
Okay.
Yep. Okay, so that's Claisen rearrangement, where there is a case where we will not stop at the gamma delta unsaturated carbonyl, but we would go further down into, let's say, let me see this here. Let me just make this. See, alpha, beta, delta. Yeah. Sometimes you will have to tautomerize the carbonyl to the enol form. Right? Where in bulletin B, we always learn that whenever we have an enol, we want to tautomerize that enol into a carbonyl. And in the majority of the cases, the carbonyl is the major form. But in some cases, the enol would take priority when it could do resonance. Like it was part of an aromatic ring or if it's part of a big conjugated system. Right? Where this is the enol, this is the carbonyl here. Right? So if I give you let's say these three reagents. First step, NaOH, water. Second step, bromine. Third step, heat, high temperature. The first step is to deprotonate the alcohol to make that negatively charged oxygen. Right? And then from here, we're going to do an sn2 reaction where this O minus here is the nucleophile that will attack that electrophile, kick out that leaving group. And then that's going to give us this product here where this was the star, this is the dot, this is the star, this is the dot. That's the new bond between the star and dot. Where this is an allylic vanillic ether, right? This is the allylic position. This is the vanillic position. So I could rotate this to make it easy to draw the mechanism arrows for Claisen rearrangement here, right? Because when we have heat, we're gonna make that bond there, shift this double bond to make a double bond there, break that bond to make a double bond there simultaneously to create and if you want to number it to keep track of everything, you could do something like this. You can number this 1, 2, and oxygen would be 3, 4, 5, 6. That would be 1, 2, 3. There's no more bond between 3 and 4 because we broke that bond. There's now a new bond between 1 and 6 because we made that bond. So this would be 6. And then 6 and 5 would be a single bond, and then this could be the bond between 4 and 5. This 5 and 4, like that, right? Okay. Where this is a gamma delta unsaturated carbonyl, right? Alpha beta gamma delta, but we don't stop here because we see that this carbonyl form is unfavorable. We want to go back into the enol form to restore our aromaticity. So to do that, we have to deprotonate the alpha hydrogen, generate the enolate ion, and that restores our aromaticity. Right. And then you can have some acid workup step, or you could use, let's say, water, some protons first to protonate, neutralize the O minus to give us our neutral product here. Or in this case, we see that we added this specific R group ortho to the OH group right there. So this is a specific kind of Claisen rearrangement problem here, and I've always seen this show up on the test. Like every time this is like on this chapter, I've always seen this type of problem on the exam, like with the tautomerization step, right? The example I gave you earlier here, we didn't have to tautomerize here because this carbonyl form is at its most stable form. It doesn't want to go back to the enol. It doesn't want to make an alkene there, and it doesn't want to have an OH here because that enol form is less favorable. But in this case, the enol form is more favorable because of the aromatic ring. So know this problem for sure.
Okay.
Yeah. Okay. So that is Claisen rearrangement. Now let's go on to Cope rearrangement, and then we'll do some 118A, SN2, SN1, E1, E2, and then I'll go do Claisen condensation. Oh, actually, that's chapter 23. So I think we'll do chapter 22 stuff first, and then chapter 23 afterwards, because all of these other stuff are chapter 22. Have you studied chapter 23 yet, Camilla?
No, I'm finishing up 22 right now.
Yeah. Yeah. All this stuff chapter 22, and then this is chapter 23 here.
Okay. Thank you.
Yeah. All right. So Cope rearrangement is very similar to Claisen rearrangement in that it is also an electrocyclic reaction, but the reactant here is going to be a let me make sure, 1,5-diene, I think, 1,5. But this one will give you a 1,5-diene as well, but I'll show you I'll show you the differences between them. 1,5-diene, right? Let me make sure it's actually 1,5-diene. 1, 2, 3, 4, 5. Yeah, 1,5-diene to another 1,5-diene. Where if you put heat to it, these would be the arrows, right? We shift this double bond to make a new bond between 1 and 5. We shift this double bond to make a double bond between 5 and 4. We break the bond between 3 and 4 to make a double bond between 2 and 3. And that's going to give us this 1,5-diene as well. Oh, wait. To keep, let me number it the same way to be consistent. 1, 2, 3, 4, 5. And you can say this is 6. Right. To keep track of where the bonds are moving. We made this new bond between 1 and 6 from the double bond between 1 and 2, which is why there's no more double bond between 1 and 2. We broke the bond between 3 and 4. There's no more bond between 3 and 4 because we shifted that bond to make a double bond between 2 and 3 right here. Right. You could say that they are identical, which they are. So they don't usually show up in this form. They usually show up with some kind of R group attached to one of the groups. Like let's say isopropyl here and tert-butyl down here. If you react that with heat, do the Cope rearrangement arrows, this is the product you would get. Where now these are not identical molecules because the isopropyl and tert-butyl are on different carbons now. Right? Before the isopropyl was on an sp3 carbon, but now the isopropyl is on an sp2 carbon. Before, but the tert-butyl is still on the sp2 carbon, but they are different molecules now. Right? If you have no groups attached to it, then they would be identical molecules. Does that make sense?
Yeah, so basically the difference between Claisen and Cope is the 1,5-diene.
Yes. The
Okay.
difference between Claisen and Cope is like Cope is a 1,5-diene. Claisen is working with allylic vanillic ether, and on the mechanism arrows, the oxygen is included in the Claisen.
Okay.
Right. In Cope, there's no oxygen at all.
Yeah.
In the arrows, but in exams, I've seen some professors, like this is a pretty common trick that they tend to do. They do this right here. Where they put the oxygen somewhere in the molecule, right? But this, and they also make an ether, but that's not an allylic vanillic ether. So a lot of people thought this was Claisen rearrangement because they see ether and they see alkenes, and they try to make the Claisen rearrangement work somehow because the reagents for both Claisen and Cope is that they both work under heat.
Yeah.
Right, but this is not Claisen because this is not an allylic vanillic ether. It's going to be Claisen if it's an allylic vanillic ether, but in this case, we have a 1,5-diene. Like if you start number 1 here, your next alkene starts at 5 right there. So this is not the correct nomenclature numbers, but I'm just gonna do the 1, 2, 3, 4, 5 like that, and I'm gonna do 6 here just to show like what group is attached to 6, and then redraw it in this form to draw the mechanism arrows easily. So this is the template that I always draw for Cope rearrangement. Okay. The template that I always draw for Claisen rearrangement is this right here for the allylic vanillic ether.
Okay.
This is for Claisen rearrangement template. Is it like Diels order or like, yeah, Diels order, like where you orient the diene and dienophile in the correct orientation to easily predict the product. Because some professors, you know how like they or the diene like in a weird angle and dienophile and like weird angle,
Yeah,
way
you have
like
to
find it.
redraw it.
Yeah. Nice rearrangement. But you have to redraw it to see, and then you have to worry about the endo-exo rule as well, EWG. But this is like you don't have to worry about any stereochemistry here. Like no endo rule, no exo rule. It's just about the template here, like the regional selectivity here. Okay, and this is the Cope Rearrangement template where let's say this is 1, 2, 3, 4, 5, 6. Now we just attach to whatever is attached to this template. 6 isopropyl, 3 ether, 1 methyl, and then now we are ready to proceed with the mechanism. Draw those arrows in and get our final answer here. Where this is 1, 2, 3, 4, 5, 6, and then we could follow through the arrows. There's this new bond here between 1 and 6 that came from that double bond between 1 and 2. That's why there's no more double bond there. There's now a double bond between 2 and 3 because we broke the bond between 3 and 4. There's no more bond between 3 and 4. And then the double bond between 4 and 5 came from the double bond between 5 and 6, like that. And then everything else is still attached to the same atom, but they are different molecules now, right? Because the groups are different atoms now. Yeah, does that make sense?
Yes, thank you so much.
Yeah, no problem. Okay, so let's move on to 118A stuff. Elysia, did you send me your the notes for your SN2, SN1, E2, E2? I want to check them out. Okay. So I don't think she's here right now, but we can move on to the chapter 22 stuff. Let's do nucleophilic aromatic substitution with the strong EWG ortho or para to the leaving group, and the one with no EWG but the strong nucleophile or extreme heat.
Okay, thank you.
Yeah. Let's see. Okay. So let's do this one. Okay. So let's talk about this scenario, the one where we have a strong EWG ortho or para to a good leaving group. Let's say that we have this benzene ring here, and we have a good leaving group like this. And let's say that we have strong EWG like NO2 ortho or para to it, and we react it with NaOH, water, and let's say bicarbonate. What that's gonna do is that's gonna substitute the bromine with the alcohol. Right. The requirements, the two requirements for this reaction is that you need to have a good leaving group attached to the benzene. And you need to have at least one strong EWG ortho or para to the good leaving group. Right. So in this reaction here that I just showed you, there is a good leaving group. So that's good. That's checked for this requirement. and there is at least one EWG, ortho, or para to the leaving group. It's better if it's like more, because that would increase the reaction rate. And then once that's fulfilled, then we could substitute the nucleophile, the OH minus, with the leaving group to give us the final product there.
Okay.
Yep. So now, the reason why we need it to be ortho or para is because when we think about the mechanism here, the OH minus is not going to attack and do an sn2 reaction. That's not going to happen, right? Because it looks like an sn2 reaction is happening here because we're just substituting the bromine with the OH. But sn2 reactions, they only work on sp3 carbons. This carbon here is an sp2 carbon. So we can't do that right there, right? But what we can do is we can make this double bond to go onto that carbon right there. Right. So now, when I draw out the intermediate here, I'm going to draw out the NO2 out in Lewis form like this, just to show that this negative charge is stabilized by the EWG like that from resonance. Right. So I'm not going to draw out all the resonance structures here because that's a lot, but I'm going to show you the arrows of the resonance structures here and show you the importance of that. Right. Because this negative charge here can do a lot of resonance structures like these all the way around, float all the way over here, boom, boom, like that. Like you see how many arrows there are? Like there's a lot of resonance arrows going on here.
Yeah.
That will give you a whole lot of resonance structures. That means that this negative charge here is very stable. And if it's very stable, it's able to exist as an intermediate, allowing the reaction to go through. Right. So eventually this negative charge at the end here is gonna go and make a double bond here, kick out the bromine, and give us our final product like that, right there.
Okay.
Right. So the first step was, you can think of it as addition. And then the second step, elimination. Right. The first step, we added the nucleophile into the molecule. The second step, we eliminated the leaving group from the molecule. Addition, elimination, aka substitution. We added the nucleophile, we eliminated the electrophile. We substituted the nucleophile with the electrophile, like that.
Okay.
Right. This would not work with a meta EWG because let's say we are there NO2 meta to the leaving group and we use the same reagents, NaOH, water, bicarbonate, Na2Cr, CO3, and we try to do the same mechanism, attack that carbon, put a negative charge on that ortho position, right? And I'm gonna draw out the NO2 just to show you why this will not work. This negative charge here cannot do resonance with the NO2 here at the meta position, right? Because what we can do next is make a double bond here, and then that would just move the double bond either on that carbon or make a double bond here, which would force this double bond to make a negative charge on that carbon or make a double bond here, right? But it cannot like jump all the way down to that bond right there and do resonance with the NO2 like that.
Okay.
Right. So that's why this right here has less resonance structures, making it less stable. And then it's going to be unable to exist, giving no reaction.
Okay. Gotcha.
That's why we need a strong EWG, ortho or para, to the leaving group to allow for this reaction to go through. Right. Now, let me give you a practice problem on this, and then we'll move on to 118A. Let's see here. Okay, what would you predict the product to look like in this reaction? Think about the requirements and think about the requirements.
It would be the chlorine.
Uh-huh. Yep.
Because it's ortho and para, and the bromine has a meta.
Mm-hmm. It would be the chlorine because chlorine is the good leaving group that has strong EWGs, ortho and para to it. So we're gonna substitute the chlorine with the nucleophile OH, and bromine would not have would not have any reaction because the strong EWGs are meta to the bromine.
Okay.
Right. A lot of people chose the bromine to substitute with because in 118A you learn that bromine is a better leaving group than chlorine.
Okay.
Right.
Also, just to clarify, the way I know it's this type of reaction is because I see the Na2CO3 and the orthopara EWGs.
Yes. You see the two strong EWGs on the benzene ring with at least one good leaving group and some kind of nucleophile with the base to it, like that. Right. It doesn't have to be like this. It could be different. Like that doesn't have to always be there for this reaction to go through.
Okay.
Right. But to know this case right here where you have no EWG, you will see these reagents here. You either see KNH2 in NH3 liquid, or you will see NaOH water in some extreme heat, like 340 degrees Celsius, like high heat, with no EWG attached to it. And these are the reagents that you would see for this reaction with no EWGs.
Okay.
Yep. Mm-hmm.
Thank you.
Yep. Mm-hmm. Yeah. And then this one here is talking about benzyne intermediate. Intermediate. Okay. Okay. Hey, Lisa.
Hi, sorry.
Okay.
To get
That's okay. It's okay.
I was in the study lounge from 12.
Oh, from 12 p.m. Oh my God. Oh yeah, you guys have today off, huh? Usually, you guys don't have school today. It's Veterans Day today. Dang. Oh my gosh. And
You want me to take you?
dang.
Oh, sorry.
And you're studying since 12. Did you eat lunch there too, or did you eat lunch before that?
Yeah, I had leftovers from yesterday when I went downtown for Hawaiian barbecue.
Uh-huh. Dang, it's good.
Yeah, and then now I'm having miso ramen.
Oh, hey, that's so good.
Yeah.
Oh my gosh. That's so good in this weather. It's getting kind of cold now.
Yes, I'm not really up for it. I heard a lot of people are getting sick, so I'm getting really nervous.
Oh yeah. I'm yeah. You try to stay warm as much as you can.
Yeah.
Mhm. Okay. Can I see? Oh, did you send your SN2, SN1, E2 notes on the Google Drive folder?
I
Or
did
you can
it
send
on
on
the
Discord.
whiteboard. I could
Huh?
show you real quick.
Oh
It's
yes.
on the whiteboard. Wait. Ta-da!
Oh wait, hold on. Let me see this. Oh my gosh.
And
Is
then
this the study lounge whiteboard?
yeah, this is I'm here by myself.
Oh, oh my God.
So here, I learned the E1 and E2 reactions, and I learned the different things about them.
Uh-huh.
And one way I kind of learned SN1 and SN2. One, there's a song. So there's SN2 backside attacks you, SN1 carbocation.
Oh my God.
Yeah.
Wait, did you make that song yourself or
Video. So
someone?
I'm like, hey, that actually helps. And
Oh
then
my God, that's good.
I think of cation as a cat. So like what I did was I
Oh my
drew
goodness.
cat ions. And so
Uh-huh.
I think of a cat who loses like electrons from like a leaving group, and
Uh-huh.
it's like it loses the mouse. And so it's looking for electrons through some other group. But yeah,
Yes.
I could quickly send you this. Just like
Uh-huh.
the rules of like Zaitsev's and like Hoffman's
Yes.
rule, and then
Do you
like
have anti-periplanar? Is there
no.
somewhere? Oh no anti-periplanar yet.
No, I'm not sure if we're gonna cover it, but
Uh-huh.
also bases, I categorize bases as like socials, like um, like we have our SN2 preference to be like small and friendly, and like they're social, so they're easy to approach any molecules. And like for examples, like nucleophiles like OH or CH3O, and like our larger bulky groups, they're antisocial because they're hard to approach other atoms. So it would prefer an E2 preference because it's
Right.
like crowded places. So I think of them like people. And then like I don't know if you could see it, but here I have like passive atoms or like content where they just wait for an environment to like become more favorable. So like again the reference the mouse leaves and then it forms a cation. So like this one it's like they're weak like H2O or CH3OH, and that would be an SN1 preference. And then there's a
Mhm.
special case for um, E1 where it's like a little bit more complicated because there's deprotonation, but it likes to be alone. But once it's ready to be in a more comfortable spot,
Uh-huh.
then like it will be able to react.
Reactive deprotonate. Yes, that's good. And that's good that you're also thinking about the mechanism, not just how to predict the products and like the rules that goes behind them too. Hoffman's rule, bulky
So,
base. That's
right. I just need practice.
yes. Let me create practice problems for you right now. For SN2, SN1, E1, E2, predict the products for them and draw out the mechanism. And then while you work on those, I'm gonna go finish the rest of the 1ACC list I have planned today. And then after that, I'll check your work and then fill in any gaps that you're missing.
Okay, thank you.
Yeah, let's do it. But nice work, like 12 to like now. That's crazy.
Yeah, I'll show you my notes. They
Uh-huh.
make more sense if you like look at them.
Yeah. So send me pictures and then is it okay if I post them at the end of like my quarter Instagram photos, like one of the montage photos? Too?
Yeah, sure.
Yes. Okay, let's get. Okay, let's see here. Mhm. What leaving groups have you learned about? Like what good leaving groups? Have you seen OMS, OTS, OTF, or have you just seen the halogens like chlorine, bromine, iodine?
I think she mentioned them. It's like, or she has it on a list. I think I uploaded it in
Mhm.
the notes, and it
Yeah,
was one chart that had all of the good leaving groups and bad leaving groups.
right. Okay. That's good. And do you know the differences between product versus a product solvent as well?
Yeah, so
Okay.
Protic, I know like one prefers or it has like floating hydrogens and the other one isn't.
Mhm.
And I think like in certain cases, like you would want something to be either an aprotic or protic. Just depends on like um your base, I think.
Yeah, base or nucleophile. Yeah, right. Uh-huh. That's good. And I could explain that more in detail when we go over these problems, like everything, like after you try it out.
Okay.
Hmm. Let's see here. Okay, yeah, let's do. this.
Oh yeah, were you asking about strong bases and weak bases?
Oh no, I was just asking about that. I was just asking the differences between a product solvent versus a product solvent.
Or was it the good and poor nucleophiles? It was like a question you asked like a couple minutes ago.
Oh, um, like I was making a comment on like what you said about like the solvent depends on what the base is. I was saying yes, it depends on what the base is, or the nucleophile,
Oh, okay, yeah.
Because
We
some.
gave us a
Uh-huh.
list.
Wait, sorry. Uh-huh.
He gave us a list. I think you
Oh
were like,
yeah.
about certain ones that we may have been like. I think you were like saying, is it like bromine, iodine, or like which ones, or like were there other ones like special cases, or, like ones we may have not approached in Gen Chem.
Right. Okay, let's do. Okay, let's do. Okay. Okay. Now let's see. Let's give you one more. Let's give you 5. Okay. Screenshot these 5 problems, predict the product, and then try the mechanism as well. And then after I finish with the 180 stuff, let me check your work.
Okay.
Uh-huh.
Thank you.
Yeah.
You said predict the product, and then what was the other one?
Draw the mechanism, arrow pushing, like how you get to the product, like from the reactant to the product, like the arrows to get there, and all the intermediates, if there are any intermediates.
And when you say intermediates, are like the ones that are minor?
Oh, the intermediates would be like if the reaction is multi-step, like more than one step.
Okay.
Draw out all the formal charges, the the pairs of electrons you can leave them as invisible, but all the formal charges for sure. And then draw the major product, and then if it's an SN1 E1 product, they go together. Draw both SN1 E1 and label which one is SN1, which one is E1.
Okay.
Right. If it's SN1 E1. Uh-huh.
Okay. Thank you.
Yeah. Okay. So let's go on to the other half of nucleophilic aromatic substitution with no EWG. But we have extreme conditions like a strong nucleophile or high heat. Okay. So let's say we have this benzene here, and we just have a bromine, no EWG attached to it. If I were to react this with NaOH, water, and some like crazy high heat, like 340 degrees Celsius, there would be a reaction here, even though there are no EWGs attached to it. If this high temperature was not there, right, and we're in room temp, no reaction happens because there's no strong EWG, ortho or parallel to the good leaving group that we have here. But because we increase the heat here, it's gonna force a reaction to happen here. We're adding more energy to the reaction. So we're actually going to substitute the bromine with the nucleophile we have, OH, like that. Right. And here's the mechanism. It's the first step is going to be an E2-like mechanism where the base is going to deprotonate that hydrogen, make an extra bond there, a pi bond there, and then kick out this leaving group right there. Right. And that's going to give us this intermediate here. An alkyne, a triple bond, into the benzene ring. Do you think this is stable or unstable?
Unstable.
Unstable, right? Because what is the preferred bond angle or geometry of alkyne, of an alkyne?
Oh, I just thought it because it breaks the resonance, right?
It can still do resonance with the ring right here because there's still pi bonds that are still parallel to the benzene ring. So resonance is still able to occur here. Right. So resonance is not being broken here because this one of the bonds of the triple bond can actually go down and do resonance with the ring like that. Wait, hold on. Let's see this. This is p orbital, and then yeah, resonance should still be able to occur where the blue p orbitals that I just drew that are vertical and adjacent to each other, those are still parallel. So resonance should still occur here. So the reason why this benzyne intermediate is unstable is because the alkyne, the triple bond, prefers to be a 180-degree bond angle, but it is forced into this ring. So that makes these carbons strained, have high bond angle strain. So those are very reactive electrophilic carbons. So the OH minus is going to attack one of those carbons and push one of the bonds onto the other carbon to give that carbon a negative charge. Right. Now, once that carbon has a negative charge, the last step is just to protonate the negative charge with whatever proton source we have, which is the water here. Like that.
Okay.
Right. But let's say now that we have an EDG ortho to it, which is the example that he gave in lecture, like this, OCH3. And let me make the double bonds like this. That's not an EWG, so don't think about the other one, the other reaction we did earlier. This is an EDG here. But this time let's use KNH2 and NH3. Right. Okay. So the NH2 here is a strong base because this nitrogen is less electronegative than oxygen, meaning that it's more willing to give up its electrons, attack the hydrogen, make a pi bond there, kick out the leaving group, and that's going to give us this alkyne in the benzene ring here, which is called a benzyne. Benzyne, right? Benzyne, alkyne in the benzene, benzyne. Benzyne. And then these carbons are strained. And you know how when the nucleophile comes in to attack one of the carbons, the other carbon will have a negative charge. Like let's say we attack this carbon, one of the bonds is going to go to the other carbon to give it a negative charge.
Yeah.
This OSH3 here, think of it as an EWG by induction. Right. So that EWG by induction is going to want to stabilize the negative charge. So that means that we want the negative charge to be closer to the EWG to make it more stable. If we want the negative charge to be closer to the EWG by induction, we have to attack the other side with the nucleophile to get to the more stable intermediate. Right. Where this negative charge here is stabilized by that EWG by induction. And the final step is to protonate and neutralize the negative charge carbon to get to the final answer here. Right, and this is the major product, where the minor product is going to have the NH2 ortho to the EDG. Because if the NH2 attacked that ortho position, this other carbon would have had the negative charge right there. And this negative charge is less stable than the negative charge here in the intermediate because it's farther away than that EWG by induction, making it less stable. Which is why this is the minor product here, and this is the major product here.
Okay. So it'll always be meta to the EDG or
Yes.
EW.
It will always be meta to the EDG. This is still like being controversial because like it's still like being researched on. So professors are like trying to go back like on this teaching this stuff right now. This is the only example that he showed in his lecture. He hasn't shown an example with an EWG yet, so I don't think you see a lot of like problems on this with an EDG or EWG.
Okay.
Right. Let's see. And then I would also check the practice ones for sure to see like if you see any EWG for this type of reaction. And if you do, let me know. So then I could make like a rule for that.
Yeah. I mean, I've been doing the Leaven's practice problems, and the only one I've seen so far is like she has a tert butyl.
Oh, like a terbutyl, and that would be considered an EDG.
Yeah.
But it's not an EWG by induction because that terbutyl R group has no electronegative atom to withdraw electrons by induction. So it's just an EDG. So that would change up the rules. It would be something different and change up the products probably, like the major minor product.
Okay.
But Farhat, he didn't go over the EDG with an R group, so I don't think he would ask that. But we have to check his practice problems and homework for to be sure.
Yeah.
uh-huh. Yeah. Okay. Yeah. So we're gonna finish the 118C stuff with Kolbe Schmitt reaction because Claisen condensation is a big one. Like there's self Claisen, there's cross or mixed Claisen, there's
Yeah,
intermolecular
no worries.
Claisen. like Aldol is coming back here. Like you remember Aldol from 118B, the end of 118B?
Yeah.
Yeah. Aldol condensation, addition. Claisen condensation is bulky. Right. So Kolbe Schmitt reaction, your reactant is going to be a phenol. And these are the three reagents that you're going to see. Some kind of base as the first step. Second step is going to be CO2. And then the third step is going to be acid breakup. Okay. What do you predict the first step is going to be here with the base, strong base? Oh wait, do you see my screen? For some reason it's delayed on my computer.
Oh, sorry. I haven't. You're like scrolling. I don't
Yeah,
know.
oh yeah. I know. It's delayed for me too. Yeah, what the heck? Why is it so delayed?
Oh, oh, okay.
Mhm.
I mean, I have the mechanism in front of me, but it's like with the sodium, it like does some weird thing with the oxygen, causing the like it becomes a double bond.
Yeah, the sodium is a spectator ion. Whenever you see sodium, what charge do you always associate the sodium with?
Positive,
Yeah, positive charge, meaning that whatever is attached to it is
negative,
negative. So the sodium here is a spectator ion. It will not do anything in the reaction. Great. The thing that would do something is the OH minus, which is the strong base. And whenever we have a strong base, we have to look for the most acidic hydrogen.
which is
Uh,
the yeah,
yeah,
hydrogen.
the
Yeah.
hydrogen on the alcohol right there. We're gonna grab that hydrogen. The bond between that hydrogen and oxygen is invisible, but that bond is gonna go to the oxygen right there, like that. Right. And then that's gonna give this intermediate here, where this alkene next to the O minus is an enolate ion. Right. So it looks like the O minus is the nucleophile, but it's not, because when you do resonance, you're gonna give that alpha carbon a negative charge. And the negative charge on the carbon is less stable than the negative charge on the oxygen because it's less electronegative than the oxygen. So the nucleophile here is actually this alpha carbon. Right. Because if I were to draw out the resonance structure of that, which is this here, the negative charge on this carbon is less stable than the negative charge on the oxygen, making this carbon more nucleophilic, making it that the nucleophile.
Got you.
So now I'm going to bring in the second step of carbon dioxide, where this C is the electrophile because it's partial positive charge. So when I have the nucleophile attack, I have to form the carbonyl between that carbon and oxygen, have the star attack the dot, because eventually, like, this carbon will have a negative charge when we like push the double bond to that carbon to give it a negative charge. That negative charge is going to attack that carbon, break the octet rule. To conserve the octet rule, we have to push one of the double bonds onto the oxygen, and that's going to give us this intermediate here, where we have this as the star, this as the dot, and this is the new bond between the star and dot. Right, where this dot here was bonded to a double bond O, which is this top one, and it used to be double bonded to another O, but we popped that double bond onto the O to make that a minus charge right there, like that.
Got you.
Right. But notice how we broke the aromaticity here.
You create it back into an alcohol, right?
Yes. We want to create it back into an alcohol eventually. So we're gonna bring in another base to restore the aromaticity, deprotonate the alpha hydrogen between the carbonyls, make the double bond there, push the double bond to the oxygen to create the O minus, and then that O minus will become the alcohol. And this carboxylate with the minus charge is gonna become a carboxylic acid with the acid workup step. So the acid workup step is just gonna protonate the negative charges to make them neutral, giving us the alcohol and the carboxylic acid ortho to the alcohol here,
Okay.
like that. Mhm,
And just to clarify, the way we know it's Kolbe Schmitt is
mhm.
because we see the carbon dioxide.
Yes. Kolbe Schmitt is always gonna have 3 steps. The first step, acid base, to deprotonate the alcohol of the benzene, the phenol. The second step is SN2 with a CO2. And then the third step is some acid workup, H plus workup.
Okay.
Mhm.
Thank you so much.
Yeah, no problem. Mhm.
Oh, also, would you mind scrolling up to the Claisen? I just wanted to see that one more time.
Yeah, Claisen condensation or rearrangement
Um,
or
oh, the Claisen, oh my gosh, thank you.
these ones here or these arrows?
Yeah, the 1,5, dying.
Oh, this one.
Oh my gosh, yes, thank you. Right, I have a
Right.
homework problem that I want to do, so
Oh yeah. And
thank
then
you so much.
yeah, no problem, Camilla. Yeah. Mhm. Hey, Alicia.
Hi, I am still kind of working on them. I,
Mm-hmm.
I haven't been able to like identify a few of them.
Uh-huh.
Like I'm still a bit iffy on like SH,
Uh-huh.
and like what is represented below the arrow.
Right.
And
Uh,
then other ones like OMS.
uh-huh. Right. So when we look at the first one here, what's your thought process? Like, what did you do first? What did you try to identify first?
I first identified whether or not like my NASH is like a weak or strong
Mhm.
base, and then like if my leaving group is a good or bad leaving group.
Mm-hmm.
And
Right.
depending on that, I I know that it's either an SN1 or SN2 reaction because they tend to happen in like with weak bases. And then I counted the degree of my carbons. So like if it's how many carbons are connected to see like if there's enough space for an SN1 or SN2 reaction, meaning like if it was an SN, let's say like SN2, we can do a backside attack and like there's enough space. Um, that's kind of my thought process.
Mhm.
I hope.
Yeah, that's good. Your thought process is correct. Uh, that would lead you to the correct answer. Now it's just all about recognizing what the nucleophile base is, what the good nuclear leaving groups are, bad leaving groups are, and what goes under the arrow. And then once you get all those, then you'll be able to predict the product correctly. But that's the right thought process to go about these problems here.
Okay.
That's
Okay.
good. So I'm gonna help you figure that out now. Whenever you see Na, sodium, or K, potassium, always associate that with a positive charge in OChem. Right. Uh, Wait, there's some exceptions. I take it back because in 118B and 118C, you're gonna learn some reagents where sodium is a metal with a radical with no positive charges. But in most cases, sodium or potassium is going to be positively charged, right? But we don't see that positive charge. It's just implicit, like they imply it's there.
Right. It's like something we learned in Gen Chem. Like
Right.
identifying those ones are easy, and then like seeing if there's like a CH3, CH2, OH, we know that's like um a weak base because like there's more attached to it. It's not an alcohol or like a
Negative charge.
yeah, it's not a negative charge. It's
Uh-huh.
neutral.
Yeah, it's neutral, right? Whereas this sulfur here has to be negative charge because it's attached to the sodium positive charge right there.
Mm-hmm.
So our nucleophile here is the SH minus, where I don't know if this is on your list, but we consider this a strong nucleophile, good nucleophile. I think that's on your list. Like good. Let me check your list. Lecture notes.
Yeah, I
Oh,
was trying to.
you sent many photo for the discussion slides too. Thank
Oh
you.
yeah.
Thank you for that.
Hmm.
Let's see. Oh, you sent on Discord. Discord. Let me check the Discord. Okay.
Yeah, because I see an RSH. Is that one? That one's like it says it's a moderate nucleophile.
Mm-hmm. Yeah, RSH is a moderate nucleophile, and that would tend to do SN2 reactions. So RSH or SH minus, they tend to do SN2.
Okay.
RSH, SH minus, uh, moderate to good nucleophiles, they tend to do SN2 reactions. Right. The way that I keep these in mind is that SN2 reactions, they're the weird nucleophiles. Like the weird nucleophiles, like that with the sulfur, neutral amine, potassium. But the SN1 reactions, they're straight and simple. it's either only going to be water or what you talked about earlier with the weak base, the ROH, like CH3, CH2OH, or CH3OH, like just some random R group, hydrocarbon, and then OH, neutral.
Okay.
Right. And then these are the poor nucleophiles because they're neutral, bad nucleophiles. So they tend to do SN1 or E1. They go together. And then E2 are going to be the strong nucleophiles. And the strong nucleophiles, I think of a negative charge on an oxygen or nitrogen. Right? Like you can see NaOCH2, CH3. Or you can see NaOH. Something like that.
Okay.
And those are the strong bases. But we could split them into two types of strong bases: small and friendly, like you put on your whiteboard, or bulky and bullies. They're bullies.
Yeah.
Right. And then the small ones would go for the Zaitsev, E2. Bulky would go for the Hoffman, E2. Right. And then everything else, SN2. Like the weirdos, like NaCN, NaN3, RSH, SH minus, neutral amines. That's probably a weird one. Neutral amine. Because that's different than NH2 minus. NH2 minus belongs as a strong base, because we have a negative charge on the nitrogen. But if it's neutral amine, no negative charge on the nitrogen, then that's going to be considered a good nucleophile, but a weak base. Okay. But a negative charge on the nitrogen is going to be considered a stronger base, right? E2, like that, right? Okay, so now we have our nucleophile. When you see something below the arrow, that is most likely going to be the solvent. And when you see random words like THF, DMSO, like pyridine, some other thing, they tend to be aprotic solvents. And they will not interfere with the reaction. Just ignore them. They won't do anything in the reaction. It's just there to allow the reaction to go through.
Okay.
Right. And OMS is a good nucleophile. This is like the list of the good nucleophiles of leavings: OMS, OTS, OTF, and then the halogens like chlorine, bromine, iodine. So I wasn't sure if this was on your list, but I had to go back and check. But this is considered a good leaving group, OMS. Like they give it like a bromine and bromine.
Okay.
Now let's look at the substrate here, this carbon. What type of substrate is that? Methyl, primary unhindered, primary hindered, secondary, tertiary, quaternary. Oh no, it's
Secondary.
secondary. Yes, secondary. So looking at the chart, what reaction are you leaning towards?
SN2.
SN2, right? So what would the mechanism for SN2 look like here?
I was gonna say that, well, I wanted to bring my negative to the right side of the secondary carbon, so like the one that's beside it.
Oh, this one here?
I was thinking that unless I can do a backside attack. Oh yeah,
Yes.
backside attack. Yeah.
SN2 backside attack. SN2 backside attack. Sing the song.
Yeah.
Backside attack.
It'll go right behind.
Uh-huh.
That, then we also have to keep in mind that if we're doing a sn2 attack, it also it changes the stereochemistry to a dash to a wedge.
Yes, invert stereochemistry from a dash to a wedge. Yes. Should I need more space here? Right. And then that's gonna give us this final product here where the dash is a wedge, but we substituted the OMS with the SH, And then the OMS left as a negative charge there, like that. Final answer.
Right.
Yeah. Okay.
So when we have this, do we have to write out the OMS as well? Like
No, you don't have to. That's not an organic product. This is what you have to write in a product.
right.
Right. And when you're going through these practice problems, I recommend labeling what each reaction is so then like you notice more patterns, right? This first one was sn2. So then like when you do more practice, you get to pick up more patterns and it becomes faster.
Right.
Uh-huh. I need to send you that leave-ins practice problem tonight for you to practice if you have time tomorrow for your midterm. Right. But for the rest of these problems here, do them as homework, and then tomorrow's office hours, I'll do them first thing in the office hours. But to check
Sounds
this with
great.
you.
Yeah. Okay. Thank
Uh-huh.
you.
Yeah, no problem. Mm-hmm.
So like just making sure, like you said for the things on the bottom, like I mean I know you said for THF that is just aprotic solvent, but like how about the other ones? Like are the other ones that include H floating hydrogens, those are protic solvent?
Yeah, product solvent because we have H bonded to one of these three most electronegative atoms, fluorine, oxygen, or nitrogen, where we see that this hydrogen here is bonded to an oxygen, so that's a product solvent right there. And if you see like nothing under the arrow, just like water or alcohol, the base or nucleophile is the product solvent itself.
Okay.
Right. Where if you see this right here, we know there's a positive charge on the sodium, negative charge on the oxygen, but this bottom right here is neutral, but there is a hydrogen bond there, making this a product solvent, which will not do anything in the reaction, in the mechanism. So when you draw the mechanism, this will not do anything, except maybe, it won't do anything in the mechanism.
Okay.
Right. Right here as well, this is also product solvent, because we have a H bond there.
Right. So is there something that like we should keep in mind when doing ones like with protic solvents?
The solvents is the last thing that I think about when I do these reactions. The big things that I think about are like the type of nucleophile base. Like, is it strong, weak? Is it strong base? If it is it bulky or hindered? Do we have a good leaving group present? And the type of substrate. Is it methyl, primary unhindered, primary hindered, secondary or tertiary? And then you could just think about the reaction from there. You don't have to think about the solvent at all, right?
Oh,
Solvent is just there like to distract you, kind of, in
okay.
the products here.
Okay, yeah, because it did distract me.
Yeah.
Okay, thank you.
That's
Thank you.
good. Yeah. No problem, Alicia. Uh-huh. Okay. Yes. Okay. That's good. That's good. Okay. Hello. Yes. I'm going to end office hours here because I have an exam tomorrow for biochem. So I have to get studying for that. Get rid of my cheat sheet ready. And yes. Thank you. Thank you. Mhm. Okay. Good night, guys. See ya.